In this lesson, we're going to take a look at function notation, what it is, how to use it, and basically all the things you'll need to know about it. So first of all, remember that a function is a relation. It's a special kind of relation, one in which each element of the domain corresponds to exactly one element of the range. So if you've got an x that has only one y associated with it, then it's a function. If you have an x that has more than one y, then it's not a function. Function notation is just a way of writing functions. Well, I'll get to it in a second, I guess. We already know that the equation of a relation can be written using two or more variables. For example, y equals 2x minus 3. You should be used to this, seeing equations written in this form up till now. If the relation is a function, however, we can write it using function notation, which looks like this. Notice how these actually represent the same relation. The right-hand side of each equation is 2x minus 3. It's just the left-hand side that's different. Instead of y, we've swapped out this f bracket x end bracket. And that f bracket x end bracket is called function notation. And I would never read it like that normally. How I would normally say it is I'd say f at x or f of x. In other words, f of x represents the y value for a specific x value. When you think about it this way, try thinking about it this way, we know that x is an input value. So f at x or f of x means what's the y value going to be for a particular x value. So I'm going to stick different numbers in for x into this function, and I'm going to do whatever, let's look at this one for an example. If I stick different values of x into this function, so f at 2, f at 3, so replace what's in the brackets with different numbers, then I'll also, of course, replace them here in the equation. The function does certain things to that x, and then what I get is my new y value that comes out the other end of this process. And so what's the function when x is a particular value? Let's take a look at some examples to clarify. In function notation, x represents the input, as always. F at x represents the output. It's like the y value, as I just said. So if this is the function here, f at x equals 7x minus 4, then f at 3, first of all, that's how I'd read this one, part A. F at 3 means find out the value of 7x minus 4 when f equals 3. All I do is I replace the x with a 3. I'm putting what's in the brackets in the place of x in each case. So you can think of this like it's a formula. And then what goes in the brackets, like 3 in this particular case, is what we're substituting into the formula. And then I just follow order of operations like normal. 7 times 3, 21, take away 4, equals 17. So f at 3 equals 17. What does that mean? It means that when x equals 3 in this equation, y is going to be 17. I can put other values in besides just numbers, though. I could put letters in, like a, and then I'd have 7 times a minus 4, and just putting in whatever's in the brackets. Now, I can't simplify beyond this if I got a variable here, but I can go as far as I can go. I can even put a combination of letters and numbers in, and I could have this be 7 times 3b minus 4. And again, I'm just substituting whatever's in the brackets into the equation. Then I would multiply it out. I'd get 21b minus 4, and I'd have unlike terms, so I wouldn't be able to go any farther. Okay, here's a scatter plot. Bunch of points. The whole function is just represented by these 7 points. I see there's one on the y-axis as well. So these 7 points. So that's my function. That's f of x. So f of x is represented by the graph. Evaluate f at 1. Well, again, let's think about what f at 1 means. It means what's the y value when x equals 1? So here's where x equals 1. Here's the point that goes along with it. The y value of that point is -1. What's the y value when x equals -3? If I go over to -3, find the point, that would be this point here. The y value of that point is +3. So it's really just, again, you're taking what's in the brackets as your x value. If there's things going on in the brackets, like in C part, I need to simplify it first. And I'll follow order of operations, as I always would. -1 plus 2 just equals +1. Now that I've simplified that, then I go to find, again, what's 1 on the x-axis. That would be here. And I'm back to a y value of -1. But I had to simplify it a bit first. This one's a bit different. Notice how for this one we had -1 plus 2 in the brackets. For this one, because the -1 and the 2 are in separate brackets, we got a different order of operations going on. In this case, we have to find out what f at -1 is, which would be the y value that goes with that point. And so f at -1 is 1. And I find out what f at 2 is, which would be this point here, which is also got an x value of 1. And then I add them together. So order of operations is totally going to come into play for what we do. And here's just another example of it. Find out what f at -3 is. So f at -3 would be +3. The y value is +3. F at -1, f at 0 is -2. That's this one. And so I got -2. Notice how there's already a minus sign in the equation. So just like we've learned in the past, we're going to have to simplify the signs. Those two negatives make a positive, and I end up with 5. When using function notation, we don't have to use the letter f. That's the most common thing, just like x and y are most common for when we're working with equations. Other commonly used letters are g or h, but they could be anything. We also don't have to use x. Some commonly used replacements are s and t. Think about a classic math teacher type problem where I talk about driving on the highway and I'm doing the relationship between distance driven and time. Well, I might use d and t in that case. So what's the distance driven for a particular time? Maybe time would be in hours, and I could substitute different values into my equation. So that's just an example of using different letters. So here's a different formula. G at s equals 5 minus 3s. So s is my independent variable. It's like x. G at s is my dependent variable. It's like my y. I'm going to do the exact same thing as I did above. It doesn't matter that they're different letters. So I'm going to put 0 in wherever I see an s. G at 0. So 5 minus 3 times 0 just becomes 5. 2 times, well, this is interesting, actually. Let me just pause for a second because we haven't seen one like this before. Notice how this 2 is out in front of the g at 1. So again, it's order of operations. I have to find out what g at 1 is first and then multiply by 2. So I could write it like this. 2 times, and then I could put brackets, 5 minus 3 times 1. Maybe I should use square brackets to differentiate here. So this 2 is just staying out front, and I'm going to do everything to find out what g at 1 is first, and then my last step is to multiply by 2. And so what I'd get is, I'm just highlighting the 2 all the way along so you can see where it's coming from or why it's just staying like that. My answer is 4. Again, order of operations matters. In C part, order of operations again, but this time I'm going to find out what g at -2 is, and then after I've done that, I'm going to subtract 3 from that. So I'm going to put -2 in for s, and after I've done everything else, then I'll subtract 3. So that becomes 5 plus 6, and that becomes 11, and the final answer is 8. Again, for this one, they're both inside the brackets, so order of operations tells me to simplify first, and I'm just going to find g at -5. So I end up with 5 plus 15, or 20. For this one, where we've got a combination of letters and numbers, we'll just substitute. and see what happens when we follow order of operations. I'm going to put a plus 2 in for s. That means I'm going to do distributive law, and I'm going to multiply a and 2 by negative 3. And so I'd have 5 minus 3a minus 6, which gives me negative 1. If I combine my like terms, my constant terms, and then I have a term. If I combine my constant terms, 5 minus 6 is negative 1, and I've got negative 3a. I'm just using the highlighting to help people see where I'm getting my numbers from and where they're going to. F part is the exact same thing again. Just put 5 minus 3s into 5 minus 3s. So I would do 5 minus 3s, 5 minus 3 bracket 5 minus 3s. That's confusing looking, isn't it? What I'm doing is I'm putting 5 minus 3s into the original equation, which was 5 minus 3s. And then I'm going to, again, I have to use distributive law. So I can do weird stuff, weird seeming stuff like this. As long as I follow the rules of math, everything works out fine. Negative 3 times negative 3s gives me plus 9s. And what I get when I simplify my like terms, the constant terms here, I get negative 10 plus 9s, and then I've got unlike terms, and I can't go any farther. Take note of the difference between parts A and B in the following example. For h at x, 10 minus equals 10 minus 3x, do the following. So here is my function, right? Again, we're just using a different letter. We're using h instead of f, but that's still just my function. For the first one, I'm trying to find out what h at 2 is. That's straightforward. It just means put 2 in wherever I see an x. So that's going to be 10 minus 3 times 2, which gives me 10 minus 6, which equals 4. No problem. Look what's different about B part, though. It's not saying h at 2. It's saying h at x equals 2. What does that mean? Well, it means, remember, that h at x is like, when we take that thing together, we're going to take this whole thing as if it's a unit. It's like it's y. So I never separate this. That doesn't mean h times x. That's a common mistake. It's not h times x. It's just one thing that has a couple parts where we write it with a couple letters, but it still means one thing. It means the same as y, right, as far as we think about it. So really what we're just being told is that y equals 2. So I'm not going to put 2 in for x in this case. I'm going to put 2 in for y. Y, again, is h at x. So I'm going to put the 2 on the left side, and I'm going to solve it for x. I'm going to find what x is. And then I'm going to go around, I'm going to do my usual math stuff where I just follow order of operations to work out and isolate my variable. I'm going to divide both sides by negative 3, and I'm going to get x equals positive 8 over 3. For the function, f at x equals negative x plus 1 squared plus 3. Graph the relation. Okay. We haven't reviewed vertex form of a quadratic yet in this course, but here's a quick reminder. The vertex form goes a times x minus h squared plus k, where the vertex is hk. So the vertex is negative 1, 3. Remember, we always change the sign of the h, so negative 1, positive 3 here. And the direction of opening is negative 1. Or a is negative 1. The direction of opening is downward because a is negative. And we're going to follow the normal step pattern because it's not stretched. So I'm going to go down. I'm going to go over 1 and down 1 on either side of the vertex. Over 1 and down 3. Remember the step pattern, our good buddy? Over 1, down 1. And I've got a quick sketch of this quadratic using vertex form. Okay, so there's the graph. Evaluate f at 0. Well, I could use the equation, but I could also just use the graph. F at 0 just means find the point on the graph where x equals 0. I can clearly see that it equals 2. What does f at 0 represent on the graph of f? It represents the y-intercept, or we could call it the f-intercept. Same idea. Is the relation a function? Why or why not? Well, let's think back to what we already learned about the vertical line test and what a function is. Does each x value have a single y value that goes with it? Or is there some place where we have an x value that has more than one y value that goes with it? Again, imagine sliding a ruler across this. So just, I'm going to draw a random vertical line there. But let's imagine we can grab that and slide it to the left or right. Is there any place on this graph where it's going to touch the graph at more than one point at the same time? The answer is no. Since the answer is no, it's going to pass the vertical line test, and it's going to be a function. So this is a function. It passes the vertical line test, which I write as a short form usually as VLT, vertical line test. Meaning again that each x value has only a single y value associated with it. Here's the practice questions.